Hello, and welcome to our video on orbits. The radial motion of an object in orbit is described by this equation. This is the total effective force on the particle, and is equivalent to the equation of motion in one dimension. The second term is a fictitious force directed away from the centre, and is called the centrifugal force. This appears because the object is rotating, so it is not true one-dimensional motion. If we do the negative integral of the centrifugal force with respect to r, we get the centrifugal potential. This potential is positive, and a stable circular orbit corresponds to its minimum. Gravity is an example of an inverse square law of force, which means the force can be written like this. In the case of gravity, K is minus gmm, giving us this. We can find the potential energy by integrating with respect to r. We set c to 0, so that potential energy is 0 as r goes to infinity. The total potential energy can then be found by adding this to the centrifugal potential. If we start with the equation of motion for an object in orbit and let u equal 1 over r, we can get this equation, which can be solved to give this. We set a is greater than 0 and theta naught equals 0, so that theta equals 0 corresponds to the distance of closest approach. If k is negative, such as in the case of gravity, the force is attractive and the trajectory curves towards the centre of the force. If k is positive, the force is repulsive and the trajectory curves away from the centre of the force. This equation is of the same form as the general equation for a conic section.
Great, we've mentioned conic sections, but what does that mean? A conic section is the 2D shape you make when you slice through a cone. Because these two equations are very similar, we can conclude that orbits usually take the shape of a conic section. Now imagine we have a planet orbiting a star. Through time, it moves through an angle theta at a radius r away from the focal point of the orbit. When it reaches the point where theta equals pi over 2, the radius is equal to the length of the semi-lattice rectum, also called h. And yeah, I didn't choose that name. Jokes aside, we can use these two formulae to obtain an equation for the eccentricity of the orbit. That's the e in that equation earlier. We find that the eccentricity is specifically dependent on the energy of the orbital system. But more on that later. Right, so we now know what we mean by the terms semi-lattice rectum and eccentricity. We can use these to determine the two final components of our orbit, the semi-major and semi-minor axes, A and B. And then we have everything we need to understand our orbit.
Orbits come in three distinct types, each corresponding to one of the conic sections. Elliptical orbits are the most common of the three. They are closed orbits with an eccentricity that is smaller than 1. Objects in this orbit have energy that is smaller than 0. Circular orbits are a particular case of the elliptical orbit, having the semi-major and semi-minor axes equal to each other. Parabolic orbits only occur when an object reaches escape velocity. This kind of orbit has an eccentricity equal to 1 and energy equal to 0. Finally, hyperbolic orbits have an eccentricity that is larger than 1 and energy that is larger than 0. Objects in this orbit have completely escaped their orbital parent, going with a velocity larger than the escape velocity.
But wait, there's more. Another way of understanding orbits is by looking at the effective potential. It can be calculated using this formula, and when plotted looks like this. So, as you can see, at energy smaller than 0, the energy line crosses the effective potential at Rmax and Rmin, the sum of which is 2a. At energy larger than 0, we have a hyperbola with an Rmax that tends towards infinity. For energy equal to 0, we have the same thing, but with 0 kinetic energy at infinity, giving us a parabola. So, now that we know how orbits look, let's find out how they work.
As we previously discussed about the eccentricity of an ellipse and other behavior of the orbits. Now, I'm going to talk about the Kepler's 3 laws. The first law states that the planet is moving in elliptical orbit with sun at focus. This can be proven by using polar coordinates and the radial equation of motion. The derivation can be quite complicated. The result is a polar function of an ellipse. The second law is a radius vector sweeps equal area in equal time, because when the planet is far away from the focus, the planets move slower to compensate the additional length of the radius. The mathematical derivation is shown below. The third law is square of period of rotation is proportional to the cube of semi-major axis. This can be proven by using first law and second law. So now you know what orbits are, what they're made of, how they look, and how they work.